Today I'm going to speak about hardware attacks, invasive attacks, semi-invasive attacks, but what I want to show you today is reverse engineering tools, because I think this is the next step, the next spread and everything for the next years. So let's see that. I will just speak a little bit about me at the beginning, just to say that I've been working inside this field for the last 8 years. And the thing is, I'm not so interested into the exploits. What I really like is finding the techniques, finding all the ways, the processes, and make them better to reach the results. So therefore, I was involved in quite some project, like optical system setup, but also sample preparation, delayering, imagery, software development, everything that can be used for. Does that work? No. For a semi-invasive attack, for invasive attack, but also for different things like photo-emission techniques or atomic force microscope techniques or even electric glitch, even if I don't do this so often. So today I will speak about hardware reverse engineering in the way that I want really to exploit, to transform the pictures I can make from a chip to a netlist and start working with it. So before I will do this, I will just go back to the past and just explain some of the techniques that are still used by the pirates as well as the evaluation lab, to be able to classify chips, in fact, because I will try to tell you what I think is the security level of the chips today, and with new tools such as the one I will present to you, the whole thing will change. It's my vision of the future. So let's see that. So let's start with Let's start with the past. I mean, it's still techniques that are used today, but they come from the past. So at the really beginning, the only things you can do to the chip was non-invasive techniques, because you didn't have access to the chip itself. So the only way you could do something is by just playing with the signal going to the chip. So most of it is clock or VCC signal that you are changing in order to make the chip do something that is not the normal execution. And out of this, you had to find an exploit to just extract the full code, for example. But these techniques, it's a lot of trial and error, and I don't like it so much because of that, because you spend so much time trying to find the good shape, the good timing, and everything to extract the code that it's just losing time, you know. And the latest chips, you can try this kind of method, so playing with the clock or the VCC, and it will not work anymore. So people get access to the chip right after that. So it's really easy to access the chip. You can just use some chemicals, and you will have access directly to the chip. Or you can just remove the chip from its original package and put it somewhere else to perform all kinds of attack, like, I don't know, fibbing or laser glitching or whatsoever. And if you are lazy enough, you will find that you don't need so much to open the chip, because especially with smart cards, if you have a Dremel tool, it's okay, you can reach the chip. And this is what I like. So once you get access to the chip, you will go into a semi-invasive attack. In the past, some of the chips were just locked with a security fuse. And if you were just using UV light, you could just erase the fuse and the chip was unlocked. So you take the data out and that's it. It's not like this anymore, but you can continue to play with light on the chip. And the wavelength you will use now is 1064 nanometer. At this wavelength, when you shoot at the transistor, you are capable of making it switch for a short amount of time. Therefore, you can change register values or do whatever, you know, you have an effect. And the nice thing, I mean, you can perform this from the front side of the chip or from the back side. And from the front side, it was very easy for chip manufacturers to prevent the technique to work just by putting a metal plane. And it was stopping the laser. You couldn't access the transistor, and that's it. But the 1064 nanometer laser, if you put it on the backside of your chip, the silicon bulk is transparent at this wavelength. It means that you can just shoot from the backside, and the laser will hit the transistor directly. So there's no metal plane or no lines or no whatsoever. You go directly to where you want to go, and you can inject the fault. So this is the principle. What you were doing at the beginning is fishing. So fishing is long, you have to be patient, but it's working. So the basic idea is you take your laser, you put it somewhere, and you just fire, and you look what's going on. Hopefully you will have an effect. So you will have an effect, and if you can repeat it and you can study it more, maybe you can find an exploit. This part is very difficult. I never saw an exploit with laser attacks, but I'm sure it can be done. So you're fishing, and this is again trial and error. It's very long, so the next step will be just to buy an XY stage, just to be able to scan your chip. So now you choose a specific timing of the execution of the program, and you just scan every point of the chip, and you make kind of a pass-fail test by looking, for example, at the data that are outputted by the chip. And if it's a fail, you just mark the position as something, and continue to scan. And you can do this for different timings and get some kind of maps of what you just did. So in this picture, you can see, for example, there are several colors because there were several effects. At the bottom, the picture at the bottom, it's transistor that you see. It's with an optical microscope, so it's really low resolution, but just to give you an idea. But then, if you want to go even further and you have quite some money, you can buy another machine, which is a scanning laser microscope. So this one is a famous. It's a very nice machine. You can use the laser now to make a picture of the chip. So you scan with the laser, and you make a picture of the chip. Once you have the picture, you tell the machine, I want the laser to be here. And so now it will be very precise for the localization. So the only thing now you have to do is find the good timings and the good spots. I mean, this is the thing. So in this picture, it's between quotes, the blue spot is a photo emission spot. You can use this to detect some structures on your chip that could be very interesting to look at, because in fact, the transistor, when it switches, it emits lights, photons. So you can maybe just look at your chip, and I know that at this position, some signal is just switching very fast. So that's one point where I want to put my laser and try to do something, just as an example. So in any case, as I was saying, it's very hard to create an exploit from a laser attack. So you want to access techniques that are working more reliably. So you will go to invasive attacks. So instead of just acting without touching the chip, now you will touch it. You will modify it. You will edit it. So, for example, on this slide, we can see 3 different pictures. At least there is a video where I want to contact a line, which is at layer -1. So I go in between the 2 lines that are on the top, and I just contact my line and make a pad. And then I can just connect to the pad and do whatever I want. On the second picture, it's just, I wanted to have some space to reach something that was below. So I had to cut the 2 lines and just replace them on the side, and the chip will still work. And the last picture is all these crosses are probe points. So there are 16 pads just to put needles on a bus and get the data. So this is very nice. This is very powerful. But if you want to do this kind of work, you have a lot of preparation to perform. The first step would be to delayer the chip. So the chip is just several layers of interconnection, and the last layer is just the transistor, the active areas. So if you want to study it, to reverse engineer it, you need to image them, image all the layers, and this is the key, in fact. This is the key. How do you deprocess the chip to have the perfect picture of 1 layer only, and how do you put them together? So for 1 layer, and then align all the layers together to have enough data to start to work. So this is the key. So before, to make some pictures of the chip, we were using the optical microscope. And I'm trying to push people to stop using them. It's not so easy, but we will see why after. I want them to change to the electron microscope. With this kind of microscope, you can make pictures. It's not so easy to set up if you want to have a real high-resolution picture, and even if you have high-resolution picture with this machine, with latest chip, you will not have enough resolution to see the structures. For example, you will have, I don't know, 3, 4 lines, but by looking with this machine, it will look like there is only one, you know, a big one. So at the same time, you have too much information and not enough information. Too much because the oxide layers are transparent. It means if you reach one layer and you look at it, you will see all the layers that are just below. And this is noise. This is extra information. I don't like to see it. And there is information missing because structures are quite small. And for example, the via are the tungsten plugs, for example, that are connecting 2 layers together. They are small, and I can't see them with this technique. For 2 reasons. Or they are too small, or there is a line over it. So if there is a line, I cannot see the via, for sure. So for me, the direction you have to take is to use a scanning electron microscope to get ultra high resolution, to get rid of all the problem we have with the optical thing. With this machine, you will see only one layer at a time, because the oxide layer now is not transparent for the electrons. And for resolution, this is just a gate. I mean, I see the active areas, I see the polysilicon gates, I see the contacts, the tungsten plugs. I see everything, so I feel all right because I have a lot of information on my picture and I don't miss one. So once you did the right choice and you scan your chip this way, you can just put pictures together and you can start to study things. So this is a very, very basic example where on the top you have something like spaghetti lines, which is the core. At the bottom of the picture, you have something which is very ordered, which is a memory. And in between, you see 2 blocks of 8 identical structure. And if you look at just some lines, you will see that those are just the buffers for writing and reading to the memory. So if I want to read this particular EEPROM, I know already where is the data bus. So I know that I will play on this. And I will find my point of interest according to this picture, for example, and then I will go to the fib. So this is another example. So it's each step of the process. So I wanted to contact one line who was lying under a metal plane. So first picture, I just removed the passivation, so the oxide layer which is protecting the chip, until I reach this plane. Second picture, I remove the plane. Third one, I just deposit oxide on the side of this hole because I don't want to make any shorts later. So I put some oxide, and then next picture, I just continue to etch my chip until I see the line I want to connect to. As soon as I see it, I just have to put some tungsten and make a pad. So after I can create another connection and isolate them properly to make sure everything is fine. So that's the basic process. And once I have this cross, I just go to the probing station and I put just some needles on the cross. And with the needle, I can just read signal or even inject signal to modify execution of the code, for example. So that's the basic concept of invasive attack. But I want to focus more on one technique, which is called linear code extraction. At least some people call it like this. I do. It's called linear because we will extract the content of the ROM from address 0 to the full range of the memory. How do you do this? It's pretty easy, in fact. We will take advantage of the way the processor is designed. I will make sure the processor is only executing sequential instruction, no jump. So it executes an instruction and just increment the address, next one, and increment the address, next one. So it's linear. If I start at 0, it will just count up until I have read everything. So I will just maybe put an example. It will be more easy to understand. So it's the chip we already saw. And what I was doing, I was just cutting the data bus and make a short between all the lines and connect that to ground. So now the core is seeing an up instruction. The only thing this chip can ever do is NOP. It's not so much, but it's a sequential instruction. So it means if now on the probe points I put my needles, what I will see is just the code that was stored in the EEPROM. It will be linear all the way through. And that's something that is still working today and used a lot, you know. So you can have a different view on this technique by just looking at the buffers. Because if you look at the buffers, you will fib less, no short, no connect to ground thing. You will just use the control signal of the latch to control the linear code extraction. You can start it when you want. So if you have a memory management and you have to wait a jump to start to be linear, you can. But you can also use the needles to inject signals. So you can skip instruction, change the instruction, or do whatever you want. You take control over the chip. So we will see this technique a lot because you will see that this example is cool, but it's not like this in real life. I mean, not so often. So therefore, I classified the chip. It's my point of view, but for me, there is three things. There is the weak chip, where maybe you can find a glitch that is working, a non-invasive attack, and you can just extract the chip like this. Or you can just make what we saw, a linear code extraction with a very basic technique. Weak. Adequate. Adequate is the level of security that everybody must have. If you want something, it must be like this, meaning that all the non-invasive attack will not work. And if you want to perform a linear code extraction, it will be harder than what we just saw. You will have to go inside the core and search for the points of interest that you want to connect to. And at this stage, we will see that you need something to find the spot in a reasonable time. And then there is the advanced security level, which is the same, in fact, as adequate. But on top of that, they put inside the chip, for example, custom hardware functions. So it means that even if I extract the memory, I don't have all the information, and I cannot, for example, clone the chip, because I missed some information that are just transistor around. So in that case, if you want to clone the chip, you really have to reverse engineering the whole custom hardware logic, so to find it and reverse it and just copy it somehow, somewhere. These three different levels are from the chip manufacturer side. For pirates, I would call them trivial, because just it's a piece of cake. I'll do it so fast. And then the adequate thing will be tricky. I mean, some pirate can do, but now we have only some groups of people, but it's not so much. And then the advanced techniques, for a hacker, it's a problem. So they will have some difficulties. But if you go to the customer side now, it's different, because it really depends on your application. If you want to have a chip for 10 years in the field, or if you want to change them every 1 year, and depending on the size of your market, and the chance that you are going to be hacked, the whole level of security can just, fluctuate a bit. So here you need really a risk analysis and so on, So in this kind of risk analysis, the question the people are always asking is, what is the next threat? What's going to happen? Because the situation at T0, we know it, but in 2 years, I don't know. We have to figure this out. And my answer is, there will be reverse engineering software around, and we have to take this into account right now, because it will be a disaster. And the thing is that everything that was already done is going inside this direction. So there's two things. There's the evaluation techniques that evolves, but also the preparation technique. The failure analysis techniques evolved a lot. So if now you have a tool that can combine the two things, the new opportunities, the new possibilities are just huge. So that's what we are going to see. Let's go back to laser fault injection. I was showing to you that you can just fish, go and try, and maybe you will see something. This thing becomes so big, it's a threat which is big enough that it's part now of the common criteria, so in some places, and therefore they test to see if you can exploit or do something to the chip with the laser. So what they do usually is they just choose some parts of the chip, like registers or output of memory, just to perform the test. But at the same time, we just saw that if you fish, you will be successful too. You will not focus on this part, the register and the memory output, but you will study them, but you will also study the core and everything. And the effect is very hard to predict. So at this stage, when I was doing the test, I wanted to know what's happening, you know, because I was firing with my laser and see strange things and couldn't explain it. So just to illustrate, this is two examples. On the top picture, I put a huge red rectangle. It's a nice zone because it's an output of memory, but the output of RAM, and I guess the register were inside. So I was just resetting my chip time by time and looking at the answer to reset. And if I was firing inside at the good timing, the length of the ATR was changing. And of course, depending on the location, I was affecting a different bit inside the value of the length of the data that would be outputted. So I could see that maybe on the top I had few bits, and on the bottom I have a bunch of bytes coming out. So this is what they will see when they will perform this common criteria test. On the bottom, I don't know how is the picture. If you can see that, yes, you see that there is green cross, a blue cross, and a red cross. It was very interesting on that chip because I was using the chip in user mode, and when I was putting the laser on the green spot, I had no timing issue. I don't care about timing, but just shooting with the laser, the chip was going back to super user mode, which is cool. And the thing which is even nicer is the red cross, because if I was now putting the laser on the red cross, I was going back to user mode. So you can just switch mode like this with the laser. And there's this blue cross. This blue cross is just if you want to skip an instruction. Just fire there, it will skip the instruction. Cool. But the thing is, it's phishing because the green crosses and the blue cross are inside the core. So I don't know. What I would say is I have no idea of what was going on inside the chip, but I had a really nice effect. Just for that reason, it was maybe 6 years ago, I wanted already to have a software to reverse engineering the core, just to understand what was going on, because to make an exploit, you have to understand. It's much better. So this is just semi-invasive attack, but let's go back to the linear code extraction I was presenting, because things are not like this all the time. This is a weak chip. But the adequate chip, for example, you will not see the multiplexer at the output of the memory. You will just see lines going to the core, and now you have to deal with it. So on this example, it's another chip. And in the middle, I just put a picture, which is a SEM image, electronic image, just to show you what was the output of this memory that you see on the top of the chip. So there were 32 lines going directly to the core. And for sure, it's an 8-bit processor. If I take the 32 lines and I just plot them, I will have some data, but I don't know what I will do with them, because I don't even know if it's encrypted data or if it's in clear, and then it's swapped, for sure, or maybe not. But there's a lot of questions to answer. So what you do in that case is you just follow the lines, and you go inside the core, and you find some gates, and you start to think, and to try to look for your points of interest. On that chip, we had 3 choices. So let's go. That's mine, maybe. Sorry. The first choice was, the first pass was leading us to a situation with the 32 output lines ending with only 1 line. So for sure, it's not the good points, because it's not a 1-bit processor, it's an 8-bit processor. I want to find 8 registers where the data are unclear. This is my goal. So second pass, on the bottom left, we found the registers. There is 8 registers, awesome. But the thing is, there is only one output because they are chained together, and there's only one output. So no, it's still not the right one. So it's always like this when you have free choice. The right one is the last one. The last one, we found the multiplexers, and just after them, registers. So at this stage, you have the register, and you know that you can just make the linear code extraction the same way we saw, but at this point, inside the core. So just looking at all these things was taking some time, a lot of times, because we have to follow the lines, the 3-pass, test. It was taking months, you know, and it's very long, months to extract one chip like this. It's very long. The funny thing that this chip was not even encrypted, so it's super easy, but no, it was taking too much time for me. So this, just to show you that, again, there's a need for software to do the same thing, but faster. In the real world, the memory are not like the one we saw. They are scrambled, they are crypted. There is everything, every feature you can imagine. And you can also have hardware custom function in some chips, some few features like this that you want to study. So you need a reverse engineering software. But in a way, you already have it, because what you can do is read ROM. For 8 years, I read some ROMs. So this is some pictures with different techniques, different kind of ROMs, just to illustrate that. But you have to read them. So to read a ROM, usually what you do is you prepare your chip to reach the bits, and then once you have them, you take the picture, you scan or whatsoever, you put the pictures together, and now you write a software, or there is some, I didn't know, but there is some, and you select the points to compensate the rotation. Your tilt compensation also is important, so you have an affine transform to put in place. Then you have a lot of parameters to set, spacing between the columns, between the rows, the size of the area of interest, and then a method to detect the bits. So it can be an average, or I don't know, something, you know, threshold or whatsoever. And at the end, you can extract just the binary. That's old school. The thing is, the ROM are getting bigger. So on the top, there is a ROM, complete ROM. You can just put everything together. But on the bottom, this ROM was just like 5,000 pictures like this, and there's no way that somebody can just put them together. Or if there is some, I want to see it, but anyway. So you have to think of a better way to extract this ROM, for example. And the best solution is instead of detecting the bits on the full ROM, you will detect the bits in each picture. But now we are going to see some of the principles for hardware reverse engineering software, because how you do that? Well, for some ROM, the bits are just via or not via. Tungsten plug or not tungsten plug. And the tungsten plugs on the same pictures, they are pure white. So it's very noticeable. So you can just tell your software, find me all the white spots on the picture. So it will find it. You will have the position of all the bits that are white. And from this, you have a grid. So it means if you have a grid, if somewhere at the crossing of the grid, there is no white spot, it's the other value. So if it was 1, it's 0. Anyway, you have everything. So you have all the bits for one picture. And you do this for the 5,000 pictures. And what you correlate now is not pixels together, it's bits together. And this is faster, less errors, and easy. I mean, it's something that is very straightforward. This is the basic principle for everything. Because on a chip, every feature that is lying on the core, for example, is on a grid. There's a grid. How do you design a chip without a grid? It would be very insane, you know, like how do I place the things, you know? The things have to match on different layers and everything. So they use a grid. So the trick will be to detect the grid, as we just did on this ROM. And when we have the grid, we can do a lot of things, finding features and putting them all together. But before doing that, you must have the perfect picture. And this is not so easy. Before, 8 years ago, when I was doing this kind of things, I was using a plasma etcher, and I was thinking, oh, it's so cool. Plasma etcher, it's a machine where you can create a plasma, and depending on the gas inside the machine, it will etch away the oxide layer or the metal. So it's cool. I remove the oxide, I see my metal, I take pictures, I remove the metal, and I do it again and again and again. But if you do this, you will not succeed, because each time you remove metal, you have the shape of the metal line that is staying on your chip. And now you do oxide etch again, and you just increase the shapes everywhere on the chip. So, for example, here, on the right side, you have a shield, and on the left side, you have the same area, but 2 layers down. What you can notice is you continue to see the shield lines on that pictures. It's noise and it's very bad. It was 2 metal down, so if there was overlayer below, it would be even worse. So you have to find something better. And the better thing is using, for example, the plasma etcher, but also CMP. So CMP is a chemical mechanical polishing, and also wet chemicals, and combine all the things. If you do that, you can have perfect pictures of all layers. And you can go in the SEM, and you will not have any effects. On the pictures, you can also see, I can show it, that you have the white dots. So you see also the via that are going under. You see them, but they are blurred. So you need to find a way to see them perfectly. And the thing is not so hard, in fact. We solved that problem by just removing the line. So if you remove the line, you still have the via. The via will stay because, for example, you have aluminum lines and tungsten via. So if you remove the aluminum, you still have the tungsten. And if you go to the SEM, on the right picture now, what do you see? You see 3 colors. One for the oxide, one is the shape of the line, it's black because the electrons are going inside the hole, but they cannot escape anymore, so it's black. And then you have the tungsten plugs that are white. So 3 colors for 3 different kind of material. This is nice. I like it to see things like this because you can just detect things. So from this, you think you can just extract every information from the pictures, but now you discover something bad. The same picture are distorted, and a lot. So I don't know if we can see here, but on the right side, you have a red rectangle showing the dimension of the transformed picture, what it should be if there was no distortion in the SEM. So the distortion is a problem when you want to put the pictures together, because they will not match. And if you have 5,000 pictures, 10,000 pictures, or even more, and you want to put them together, they have to match. So you don't have another choice than just reversing the transformation and transforming your picture to be able to stitch them together. So when I take a chip, first thing I do is I will just scan it and import it inside my software and just choose the area I want to study. So for example, the core. I don't see what's going on. Yeah, so you will see, I will just mark the picture I don't like. I don't want to study all of this, so I just mark them. Like this, the software already know, this is bullshit, I don't look at this. Next step is detecting the thing which is obvious, so the white spot, the via. So I just set some parameters. I guess it's very slow, huh? Let's be faster. So I will just, I'm setting up some parameters, so it's maybe 30 seconds to find the right one, just to identify all the via on the chip. And your algorithm must take also into account that there can be some dust on the chip, and these are not via, so you have to deal with the size of the via and everything, etc. Then you say to the software, find the via on all the chip. So you will do it, you can just check that everything is fine. And once you have all the via on the chip, you can reverse now the transformation, the distortion of the SEM, because all these via were lying on a grid. So if you put all of them together now, and you try to align to a grid, you will create a map of the distortion of the SEM for your scan, which is very cool, because now I can transform the pictures back, blah, 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 lots of things. So once I know also the position of the grid, I will try to detect my lines right now, because I have an extra feature. It's the lines are staying also on the grid. So if I know already where the grid is, it's faster to just look at this point and say, is there a line here? Instead of just looking for a line somewhere in the pixel mess, you know. And at this stage, I don't have pixels anymore. All the information of the picture were transformed into polygons. And polygons are very useful, because now what I will correlate is polygons on a grid. So it's like the ROM before. We wanted to extract every picture and put them together because it's easier, but it's true also for the core. So at the end, you stitch the pictures together, and the worst case scenario here, there is 3 pictures, and it's very, I don't know if it's noticeable, but the worst scenario is the lines are jittering a little bit around the grid line because of the detection mechanism. Where is the line detected? Okay, it can move a little bit 1 pixel off, or I don't know. So anyway, when everything is stitched together, you can still verify that the correlation went fine just by playing around, you know, just reviewing your picture. And you see that it's not moving pixel by pixel, it's moving on the grid. Because everything now is grid related. So you review all your pictures. You can also look if the features have been detected properly. And just after that, you have to align 2 layers together. And this is very easy, because now you align 2 layers that are lying on the grid. You have a bonus now, because you have used this principle. You can use a magnification which is very low for the top layer, because the lines are big at this stage. And then you can use a very high resolution for the bottom layer. But when you want to align the 2 layers together, you don't speak about resolution or magnification. It's grids that you align. So it will align perfectly. And you will have no error of stitching for 1 layer and no error for the alignment of the layer. And basically, once you have this, as everything is polygon, you can just convert this to a netlist. And now you have the netlist of the full core. Yeah, this is summarizing what I just said. For the gate detection, I don't show gates because it can be an issue. But the gates are detected with the same kind of principle. Detects features and just perform some mathematical operation on the results, you know. So no more polygon, no more pixels, sorry, polygons only, netlist. Once you reach that point, you have now a lot of information about your chip. In fact, you have much more than what you need, really, if you want to make a linear code extraction. It can be overkill to have the full netlist of it. But you have a lot of information, and you can do a lot with it, really a lot. It can help you in ways for semi-invasive attacks, for example, because instead of just phishing somewhere, you can just have this full netlist and look inside it and find what you want to do. You can speed up your linear code extraction preparation because you know what you're looking for and you have all the information in front of you. Instead of making shield bypass, so the shield is the upper layer, for example, and it's a structure which is just there to prevent somebody to cut a line. If this line is cut, for example, the chip will just erase its contents, which, by the way, can be prevented if you disable the charge pump. But anyway, so instead of just trying to mess up with the shield, if you have the netlist of the chip, you can just go to the place where the shield is saying, okay, I'm all right, or I was just cutted. And you can just fib and say, okay, all the time. And now you remove the shield. You don't care anymore. There is also over embedded countermeasure that you can bypass. It will be long just to go through all of them. But you can do even funny, even better things. This is a dynamic voltage contrast. We use an electron microscope, and what we do, we clock down the chip, and what we see now is if the line is white, it's a 1. I don't know, 1, yes. And if it's dark, it's a 0. So basically now we see the chip running, but it's not so useful if you don't know what are the lines. But if you have the netlist now, you can study that. So you can know okay, I have my lines, and maybe I have a bus over there, and I know where it is. So I will not even put a needle to extract the chip. I just look at the screen, you know. So this is something which is very nice, and there is also other techniques that can be used now, like electromagnetic attacks. I was never doing this, you know, but I think now if I have the ability to spot some places, why not? I can try. At least it will not be fishing. I don't like to fish. Other thing, it's another bonus. As you have all polygons, you can just create a GDS2 file on your chip and just provide it to somebody. So it means this guy can just take this file, put it inside this focus ion beam, and just navigate from it. So it's even better because now the chips are planarized on the surface. So it means it's very flat. And if you look at it under the fib, you see only a dark thing, you know, just dark. You see nothing. So to find the good place, you have nothing to rely on. But if you can just overlay this, now it's okay, it's all right, you can work. And if you want to do a backside edit, you can also use this kind of things, you know. You will make one picture, maybe with an infrared camera, to have an idea of some positions, and put that on top of it, and now you can just navigate and find the things. All right, if we go back one more time to laser attack, we can change the way we were fishing. So instead of just trying every position and see if I have an effect, I can say, where are the registers inside the core? Because those registers, for sure, if I shoot at it with the laser, I have an effect. It's 100% success. I will have an effect if I shoot at one register. So I can just ask the soft, show me where they are. So it will show you the nice position for you just to test your attacks. But you can still fish. And if you find something very interesting now, you go back to the netlist and you say, okay, what was going on? And you can start to study things. So I guess it brings you so much knowledge that you can start to think of different attack scenario, etc. And the risk is that now these kind of attacks are getting much cheaper. So we spoke about the $1 million machine, but if I wanted to go in laser attacks right now, I would prefer this do-it-yourself solution, which is maybe, I don't know, 2,000 or 3,000 euro, and you will have at least the same possibilities, because you have the netlist again, because you know where you are going, you know what you do. So that's a huge threat, because we go from $1 million equipment to $2,000 equipment, which is nice. We saw already this picture, but it deserves to have its own slide, because here we saw a register, and they are just chained together. And what can it be? It can be JTAG, for example. And now imagine there is the JTAG thing. I just found it, a chain of register inside my chip, and usually it's disabled. So I will just look at this and try to see if I can just enable it again. And if I could, it's now a disaster, because I have access to everything inside the core. I'm basically now the master and saying, do this, do that, extract this, or, you know, it's a mess. So this, nobody's doing this right now. But with the ability to study the netlist, now it's feasible. In 2 years, this is a huge threat, because the chips are getting complicated, so we need a scan chain, a JTAG, I don't know, and if somebody can just put it back in action, poof, it's he will have some fun. Anyway, just to illustrate how the work can be changed with the software, we'll take an example. We will take a ROM chip, which is scrambled and encrypted with multiplexers and buffers deep inside the logic. And the encryption will rely on the address, which will be scrambled also, and all the things. And we will try to see with the old process and the new process, how long do you need to just find a place for linear code extraction? And also we can just take this little encryption thing to see it as we can see it as a custom hardware logic function, even if it's very little, and we can just see, can we just find it out and extract the ROM just by taking picture of the ROM, the encryption, and putting this together in a simulation and just get the ROM in clear. So the whole process, you take your microscope and you start to correlate the things with the software based on pixel values. You will have a lot of errors, so you will end up in Photoshop putting the things together on different layers. Like this, you can just adjust if something is wrong, you know. And it's not so nice for me, but you will have maybe 500 layers for only one layer of the chip, and now you have the other layer that you want to put in place too. And so you will have 500 layers times the number of layers of the chip to deal with in Photoshop. And you will not succeed to align two layers together. Why? Just because your focus will not be the same, or the magnification will change a little bit, your tilt setup is not good enough, or there's a lot of possibilities to have this wrong. So to align the two layers together is not feasible. It means you will also make some local adjustments. So you make local adjustment everywhere. And now what you do is you trace your lines by hand, I have a line here, and a line here, and here a line. You have to go from layer to layer, find the gates, identify the gates, write down what it is. And it's huge. We are speaking about huge. In that case, it's only 1,000 gates, but still, and you will start to draw a schematic somewhere, not to get lost. And if you do it with paper, you will have paper everywhere, with schematic. But that's not enough, because if you want to simulate it, your schematic is not so usable. So you will write somewhere all the equation, all the netlist by hand. So you will make errors, because you just take your schematic and you copy something. Maybe you will swap inputs or things like this, and you will have a lot of errors. Already on that example, we have a cell 313 and 313 bis. I don't know why, but I think something went wrong on this. And you have 100 pages of this. Okay. So what do? You continue. You will find the correct spot for the linear code extraction with this method, even by hand. But let's say the day you want to go to the fib, the machine is down. And it happens quite often with the fib, unfortunately. Okay, it's all right. I did all the reverse engineering things, so I can just extract the code like this, because I will just run a simulation and I have it. So you run your simulation, and the HDL simulator will complain. There are errors everywhere. So you try to fix it, and from a logical point of view, you will fix some, But if some are still there, you have absolutely no way to find them back. So you have to do it from scratch one more time and compare the two results to find the mistake. So it's very time consuming. On the other hand, I can just say I will use the software to do that. So I will do a deprocess with the techniques I was explaining to you to have the polygons version of everything. So then for each layer, I will have to correct things to make sure that everything went fine. One day per layer. So maybe I have the deprocessing and the image in 1 week, maybe 2, let's say 2. And 1 week later, I have netlist of the chip, 3 weeks. At this stage, I have no stitching problem, no local adjustments to do, everything is aligned, and the netlist is done. I mean, if now I start to trace things, the schematic is done, and the equations are written, but not by hand. It's the software. So I remove source of errors. A lot of errors are just left away, It just work. And you can have errors. I mean, it's for sure, it's hard to detect millions of features of a chip without making errors. But now, as you have a netlist, you can start to look around for your errors. It's not so easy, but at least you remove most of the error. So in that case, you will find also the points for the linear code extraction. So we did 3 weeks to have the full netlist. and let's say maybe 2 weeks later we start the linear code extraction. I would say even less, but why not? If you, with the old process to start this linear code extraction, we already worked for several months. At least 2, I would say. Anyway, if I compare now the two things, and the fact, the question is, can I just reverse the encryption function by hand or with a reverse engineering software? By hand, you can work 6 months, and it doesn't work, and you give up. You give up. It's already too much. So then you have we did a software which is kind of in between. It was removing all the errors of making the schematic and the equation by hand, but not all the errors that were done with a correlation issue and alignment and things like this. So we did the same study basically in 2 months with errors. Too bad. With the next stage, you can do the same thing, I guess, in 1 month. In 1 month, you will have the time to take the pictures, to create the netlist, to find out the spot for linear code extraction, maybe to perform it. And for sure, as you have the netlist, you can also simulate the encryption function. That was this, by the way. So the threat is huge, because with this kind of tool, for hackers, it's 100% success rate for chips that are now adequate. But the thing is, the advanced chip, they just have this hardware custom function on top of the adequate thing. But hardware custom function is just a pattern of gates put together. And if we think a little bit, a ROM is a pattern of bits that you put together. So what's the difference? There's no more difference. So it means that those guys, those bad guys, will also be able to look at customized chip. So the advanced security level is becoming adequate, and adequate is becoming trivial. So there's something to do at this stage. The issue that we will face are piracy, for sure, but also counterfeiting or patent violation, because now I can just look what you did. Show me, I will look. So this is the bad part of it. The good part is now you have the tool. You have the tools to just exploit the failure analysis techniques and the evaluation techniques, and to put that together to have something more secure. I mean, you will target already the things that are important for some invasive attack or invasive attack. Therefore, you can just, as a chip manufacturer, for example, I would go to my design team and I will take extra care of the routing techniques, the strategies, and I will change them. I will change also the way the hardware functions are implemented. So far, it's just another layer of cryptography. No, it must not be like this for the future. The thing is, we have to think of a way with these things to make the work for hacker so difficult that it will not be reasonable to spend the time and the money to do this in a reasonable time. Even with this kind of software, the part that hackers will have to do, and which is difficult, is the invasive attack itself, fibbing. So if this is becoming tricky for whatever reason, we can slow it down, and if it's enough, we can continue to have adequate chip becoming almost the advanced security level. What next? Yes, it will help also in things like patent violation studies, because you can just look, did they steal my patent? Yeah, let's have a look. Or you can just take counterfeits and just look at them just to make sure it's counterfeits. And it can also be useful in case of IC obsolescence, for example. I don't know. Let's imagine there's one chip that disappeared, and no datasheet, nothing, but it's used in a critical environment, and you want to find a solution. Why not taking it, just using techniques to emulate, to have the netlist of it, and replace it with something, an FPGA, or I don't know. There's things you can do at this stage. I will be on time. I did better. So I will just give you some words about the future of this kind of software and techniques. The thing so far, as I was telling you, is we have the full netlist of a chip, which is way too much information. If you want just to study starting like this, taking your mouse and scrolling down on the netlist and maybe a schematic that is generated, you will spend some time before starting to understand what's going on. So what you want to do is reduce the amount of information you have. For this, there is something which is very easy, because the software is extracting gates. So it says, for example, I found this type of gates 200 times on the chip. Yeah, all right. But now you can just look at the link between the gates, and you will find that this gate is always linked to this one 5 times on the chip. So they are linked 5 times. It's not something that is random. It must be a function. So you just start in from one gate, and now you have maybe 2 or 3 or 4. You have a group of gates. And now you have to study this group of gates. Instead of studying every single gate, you study groups of gates. It's better. So that's one thing, to just reduce the number of things you see on screen. And then one thing also, which is very interesting, I'm currently trying to see if I can find all the features without taking care of the grid at all. And it seems that it's reasonable. With some modification, light modification, you can perform the same thing without having to care about the grid. This is nice because, in fact, if you look at the chip, the core is on one grid, and the memory, for example, is on another one. Doesn't match very well. But if you don't have to care about the grid anymore, you don't just have the netlist of the core. You have the netlist of the entire chip, which is even worse. And I don't know. I think it's pretty much it. So for the future, yeah, we can also add very, very specific things like a simulator. Why not? We have the netlist, let's build a simulator. I don't use the HDL simulator so much because they are slow, because we want to emulate and give you insight about one implementation, so it's slow. So you can write a C simulator just to know what's going on a functional point of view. So this can be very useful too. And after that, we can have very specific tools like I want to reach this signal, can you show me, I want to do it with the fib, can you show me the best spot, to do it, or I don't know. There's a lot of opportunities now in front of you. So that's it. Thank you for your attention. If you have any question, I will try to answer. Yes? Yep. Sorry, I didn't get the second. Let me answer the first one, and we go back to the second. So the first one is, can we use this technique on something much bigger than just a little smart card or something? Yes. We were using. I was trying on a chipset that was a piece of a die, like a 1 centimeter square die, with I don't know how many transistors, but really a lot. It was 90 nanometer technology on 8 layers, I guess, and it's the same. I mean, basically, there's no, the size doesn't count. It's just you have more data, but doesn't change anything. Sorry? Yes, you mean for the timing? Not so much. I would say that I don't know. I would say that scanning the thing is something that runs overnight usually. I do this overnight. So if I have to scan 4 hours or 9 hours, it's okay. It's one night. So this time will not change so much, and you can just, it's okay. You can deal with it, and then. The thing which can belong is verify that everything went fine. You know, just verify that you just extracted the polygons correctly and everything. This can take time, but it's not critical. I wouldn't say it's critical. It's still feasible, and you will still be so much faster than everything else. You know, even if you have to spend three days instead of one on one layer, you have done at least in 2 months maybe, or 1 month and a half. It's still okay. Yeah, yeah, sure. The thing I don't like so much this puff thing, but Dimitri was writing some papers about puffs that are very nice. But the thing is, you will extract everything, but you will have, for example, a key that is missing to understand the chip, and the key will be created from the puff. The solution is to use what you was showing, for example, and just change the puff and get the key one time, and then you're fine. You're fine. So it's a different issue, I guess. It's the puff on one side, and at least on the other side. Question? Yes. So sorry.
How much would it cost to set something up like this from scratch with the
Yeah. It depends. Before, I would say that I don't know. Let's think a little bit. I would say that just the imaging part with a scanning microelectroscope can be a scanning microscope can be extremely cheap if you buy it second hand. And to do the pictures that I'm doing, I don't need something very high tech. You know, I need just a scanning microscope. Sorry. And this is, I don't know, I think I can find some for $50,000, maybe less, even less. Then you need all the sample preparation tools. There's one thing which can be expensive is the plasma etcher. But the plasma etcher, I'm using it only to remove oxide. So it means, again, I don't want a high-tech machine. An old one is okay. So if I can go on the second-hand market and find one for, I don't know, $20,000, it's all right. So if you want to put everything together and you want to build a lab, I don't know, it will be expensive. It will be a few $100,000 or dollar. I mean, it's the same. But what you can also do is just go to a company and have this serviced. You know, you go, I want these pictures, do it for me, and it will be much cheaper. And you're willing to work with. This is the nice thing, yeah. Not so much, not so much. But you can find some. Then, if you want to have also the capacity to perform the invasive attack yourself, you have to buy a fib and a probing station. It starts to be really expensive because now if you want to have a fib on the second-hand market and you want to have a nice fib because you want to do backside because maybe you will have puff sometime or things like this, it's $500,000. So no. Yeah, but the thing for the fib is I will rent some fib time. I will not buy the fib because look, you can even do the navigation layer, so the navigation file. So you go to somebody and you say, I want to contact the points. I mark them already. It does that for you. It's 1 day of work, so it's not so expensive. Yes. I never did white box. Okay. Never. And this is the thing. I think that if you want to find the weakness of something, you have to be black box from scratch. So I won't go to a manufacturer and say, give me your files, give me your net list and everything, and I will study it. I will say, no, give me the chip. I do the thing, and this way I will find stuff, you know. If you have already all the information, where do you look? I mean, it's just, no, it's too comfortable. You need to think.
Well, no, I was saying that you could use it instead of fishing, right? So
Yeah,
you
sure.
could- So instead of going through your whole giant process, right?
Mm-mm.
Sort of get all that information, and you could just continue.
Yeah, but that's true. But personally, I prefer staying as far as I can from the official documentation. Yep. Yeah. I didn't get the question. Sorry. Yes. Yeah. It's always possible. And in fact, you can do whatever you want. On one chip, there was 6 lines going outside of the chip, and we had the wafer, and we could look at many chips. And in fact, during the production, it's just cut, and it was a pattern of lines making kind of a fuse, or I don't know, But you can reconstruct that. But I would say it's even better because if you have the netlist, maybe you don't have to focus on the fuse, but you have to focus on the structure, which is saying yes or no. This is the structure you're looking for, and any embedded countermeasure, anything like this, you can just bypass.